Hello everyone and welcome to the 7th episode of Range of Science. Today our guest is Anil Seth. Anil Seth is leading researcher of consciousness. He's professor of computational and cognitive neuroscience at the University of Sussex. And today we are going to discuss his latest book, Being You, which is a very good summary of current status quo in neuroscience of consciousness, and it is easily digestible for non-neuroscientific audience. So Anu, before we delve into the current state of affairs, I would like to trace back historical development of predictive processing. Particularly to focus on a philosophical contribution. Kant famously influenced Helmholtz in unconscious inference idea. You also talk about abductive logic developed by Charles Sanders Peirce and its relation to Bayesian equation. And also let's discuss contributions from art. You discuss beholder's share and how this idea was developed not just by scientists but by artists during the Age of Insight, as Eric Kendall labeled it.
Oh, thank you, Zaza. It's a pleasure to be here, and very happy to start in this direction. This whole idea of predictive processing, which has gained a lot of prominence in cognitive science and neuroscience lately, as basically the idea that perception is the process of the brain making predictions about the causes of the sensory signals that it gets, and then using the sensory signals to update these predictions in a continuous process. That's the fundamental idea. It turns out, as you beautifully summarized, that there's a very long history in many different spheres of thinking that pick up on this same basic idea. It's not just sort of the latest neuroscientific theory that's just come about in the last few years. Indeed, Kant with his idea of the noumenon, the fact that, or the proposal that there is a real world out there, but we will never actually know what it is or experience directly what it is. It will always be hidden behind a sensory veil. That's one very strong current. And as you noted, Helmholtz seemed to be strongly influenced by Kant. And Helmholtz was the first person in the late 19th century who formalized this idea at the beginning of psychology and neuroscience, this idea that perception is a process of, he called it unconscious inference. We're not aware of our brains engaging in this process of making predictions and updating them. We're only aware of the outcome of that process. That's one very strong current, and philosophy has remained a key part of the development of this story. So in contemporary philosophy, we have people like Andy Clark, my colleague here at Sussex, and Jakob Hohwy and Monash, who take differing perspectives, but still on this same basic idea and try to use it to understand various things about cognition, perception, and action. My own perspective has been to think about what light predictive processing sheds on the nature of conscious perception, specifically on the nature of consciousness. And this then brings in some of these other areas that you mentioned, like, quite surprisingly for me, the history of art. I happened to be reading Eric Kandel's book, The Age of Insight, and he talks there about the art historian Ernst Gombrich, whose concept, the beholder's share, was indeed very influential, especially in sort of mid-20th century art theory and history of art. And it's essentially the same idea that when an observer encounters an piece of artwork, the experience they have is partly the product of the observer. It's not just inherent in the piece of art. And this is easy to say, but he sort of makes quite a big deal about this. So our visual experience, not just what we think conceptually about it, but our visual experience of an artwork is partly comprised of, as he put it very lyrically, the beholder's share. And this does sort of strike what I would call a phenomenological tone. So it's more about the nature of the experience. And I started looking at art in a bit of a different way after this. I would look at some of these impressionist masterworks, which, if you look closely, they're pretty rough. They're just palette scrapings on a dirty canvas, as the famous review at the beginning of Impressionism said. But then as you step back, this very evocative, vivid scene emerges. And why? Why does this work? Why is Impressionist art so effective at evoking a scene? And the idea here is, well, that's because that the artwork is not providing an accurate depiction of a scene. It's providing the raw materials that engage the brain in the act of making sense. And our experience is then, I think, deeper and richer because it engages more of the beholder's share this way. So there's a great deal of, I think, relevance here to the way we experience the world normally. For instance, the difference between vision at the center of our visual field and vision at the periphery. It's a very interesting difference between the two. The periphery is not blurry, but it's not sharp. It's different in some way. And various pieces of art or artists have explored this idea too, and ideas of perspective. Cubist art makes us think about what does it mean to see things in perspective. And you can link the two here by thinking that in normal vision, we experience things as three-dimensional objects because our brain is making predictions about how objects would look from different angles, sort of implicitly. At least that's my theory. And then Cubism is basically an expression of that theory in pieces of art, where we see objects from multiple dimensions simultaneously. So there's a lot of currents, even go back to very religious and spiritual ideas. The idea of Maya, that everything is illusion, I think is very central to this way of thinking. And in Buddhism, the idea that the self in particular is a kind of illusion, that what we experience as the self is not picking out a real immutable essence. And this is where I end up in the book. It's really starts with how we perceive the world, but ends up as a story about what it means to be a self and how that can be understood through the lens of predictive processing, but in this larger context too.
One might even argue that it can be traced back to Plato's allegory of cave. Do you agree with that?
I do, yeah. I use that in talks actually as like just when I'm trying to deal with the whole background to this in 3 minutes, I'll start with Plato's allegory of the cave. The allegory being, of course, for your listeners, that there are prisoners chained to a wall in a cave and all they see are shadows cast by firelight playing on the walls of this cave, and they take the shadows to be real because that's all they can, that's all they see. So we are like prisoners in another cave would be the allegory. Yeah, I think you can go all the way back to Plato, but as I was saying, I don't think it's even confined to kind of Western philosophical traditions too. I think there's almost certainly analogs to this way of thinking in all the spiritual and philosophical traditions across the world, across cultures.
One of the things I liked about your book is that you translated the idea of free energy principle, which is famous for being hard to understand for non-specialists, to relatively easily digestible text. So would you mind explaining what is free energy principle and how it is related to Bayesian brain hypothesis?
I can definitely try. It is hard to understand, and I still struggle to understand all its mathematical and formal details. Fortunately, I've got very smart colleagues who help me on this journey who are much better mathematicians than I am. But the free energy principle I found very fascinating. It's pioneered by Carl Friston, who's a friend and a colleague and a really incredibly influential neuroscientist in the UK. And I think the best way to explain it, I actually really struggled with writing this chapter of the book. In fact, I should probably confess that my editors were initially very skeptical about whether to include it at all. It might be too far a reach, but I'm really glad that I did in the end. And I think the best way to think about it is as sort of coming at the same idea of predictive processing, but from the other direction. So when we were talking about Helmholtz and Kant, it's often about perception of the outside world and how there's this indirect relationship. So the brain is predicting the causes of sensory signals and using sensory data to update those predictions. Now, the free energy principle starts in a very different place. It starts with what it means to be a thing, what it means to exist, and a bit more specifically, what it means to be a thing that persists over time, like living things. We persist over time. We're open systems. We take in energy from the environment and we make actions, but we persist as an identifiable structure, an organism, over time. How do we do this? Well, it's a bit of a challenge thinking how this happens at all, because we have this thing called the second law of thermodynamics, that all things tend towards states of maximal disorder. The technical term is entropy. Disorder increases. You break an egg and you can't unbreak that egg. There are many more states of a broken egg than there are states of an unbroken egg. So why don't we just dissolve into biological mush? And of course, when we're dead, we do, but we don't, the definition of not being dead is not doing that. And so we as living creatures inhabit a very small subset of possible states over time. And it's being in that, what we can call an attractor set of states, that defines us as a thing that persists over time. So this sounds very, very abstract, but what this means is that in some sense, we are minimizing the uncertainty of the states in which we can be. We exist in a limited set of these states. How does that happen? Well, you can then make the argument that we want to minimize the entropy of, let's just make a little leap here and say the entropy of our sensory signals, the signals that we perceive from the environment. We want to, if we're a fish, we want to be in water. We don't want to be out of water. I want to persist in states that I expect to be in, at the level of my low-level biology, not psychologically. Like, I expect to be in Brighton. I am, but I expect to be surrounded by air I can breathe. I expect to be in a state of relatively constant nutrition, and so on. So how do I minimize the uncertainty of these states? Well, this is where this strange thing called free energy comes in. Free energy is a concept from statistical physics, and it basically provides a limit, an upper bound on this entropy. So it turns out that I can't directly minimize the uncertainty of the states that I'm in, because I don't know all the possibilities. Like my brain body organism doesn't know all the possibilities, but it is possible to minimize a limit on it, an upper bound, and that's the free energy. So by minimizing free energy, I can, as an organism, and this is the idea, is organisms at some level do this, maintain themselves in states in which they expect to be in, and those are states which are consistent with being alive. Okay, so if you're still with me, the next step is, again, a little bit simple. There's some maths underneath it, but to minimize free energy, what does that actually mean? Well, it turns out, under some assumptions, it's equivalent to minimizing prediction error. So if I have a brain that's sort of set up to do predictive processing, make predictions, you get sensory signals which are prediction errors. So I can either update the predictions all the time to minimize prediction error, or I can change the data. I can perform actions that are predicted to bring the new data in line with my predictions. And that's what any kind of control system, or that's what many kinds of control system do, or can be understood as doing. They make predictions about what they want to control. Like, I want the temperature of my house to be 19.5 degrees centigrade, and they make actions like turn the heating on or off in order to make that the case. They don't just update the temperature, and so it gets hotter or colder. So to bring this together, we can understand this whole process of minimizing prediction error in perception as the manifestation of a more fundamental imperative to minimize free energy and to stay alive. And critically, when we cash this out in terms of neuroscience, this speaks much more to what the brain is doing with respect to the interior of the body. So we experience things like emotions, we experience things like hunger, thirst, fear, and so on. These are all very tightly related to the brain's perception of the internal state of the body, what we call interoception rather than vision and hearing, which are exteroception. And interoception is much more about control than it is about figuring out what's there. You know, the brain needs to control the heart rate, the blood pressure, all sorts of things. And so that, I think, for me anyway, provides the link that we can now begin to understand that we evolved and developed the kinds of brains whose fundamental job is to keep the body alive. That's a process of control and regulation of the body. That process, the theory goes, is implemented by a form of predictive processing. Carl calls it active inference, where we minimize prediction errors through making actions. In this case, these are actions the brain is taking to regulate the body. So that's already a basic loop of minimizing prediction error, minimizing free energy. And then that can be bootstrapped onto how we experience the outside world. So the reason, and this is now it's kind of a story, kind of speculation, but this is the line I take in the book, that the reason we have predictive processing to perceive the outside world is because it was already there to regulate the body. We perceive the world around us with, through, and because of our living bodies. That's the kind of core concept of the free energy principle in terms of its relevance to what I do. But it's basically a very, very wide-ranging principle that underneath which you can think of various different manifestations of it in different contexts, whether in biology or in evolution or in other things. And it's a developing framework as well. So we've been working on with my colleagues, Chris Buckley and Alec Chance and Baron Millage, on the extensions of different ways of thinking about the free energy principle that look a bit more to the future. So organisms can be thought of as minimizing the expected free energy in the future rather than in the here and now. And that turns out to very nicely relate to things like the balance between exploration and exploitation, or more colloquially, why we are curious organisms, why we seek out new information. So yeah, it's not a thing that is true or false, but it's a framework that is useful in the sense that it integrates a lot of ideas and might generate new testable hypotheses.
We can also inverse the reasoning and derive free energy from Bayes equation as a proxy to model evidence, right?
That's right.
It's been labeled as high road and low road. What you described here is high road to free energy, if I understand it correctly.
Yeah, that's right. I missed that step, so thanks for putting it. Yeah, this whole thing can be then related to Bayesian inference. Now, Bayesian inference, again, is this very generic framework. It's a way of reasoning under conditions of uncertainty, and you can often pose a challenge for an organism in terms of Bayesian inference. What is the best guess that this system should arrive at in order for some to either make an accurate representation of its environment or to control a variable in the best way? And this is a nice framework, but actually implementing Bayesian inference turns out to be very, very difficult thing for any actual mechanism to do. So the other nice feature of all this is that minimizing prediction error in predictive processing on the free energy principle turns out in many cases to approximate Bayesian inference. So it's a useful sort of what we would call process theory. It's a proposal about a mechanism that might in practice play this role of approximating Bayesian inference, which is something that is a useful way to describe optimal control and regulation in organisms.
Traditionally, integrated information theory and Bayesian inference have been looking past each other. I have discussed this with Chris Fried, and he's quite skeptical on usefulness of integrated information theory. But in your book, you write that there are some things that are too speculative about this integrated information, but some things that are useful. Would you talk about that?
Yeah, sure. So the chapter on IIT, Integrated Information Theory, was actually the other chapter that there was a bit of skepticism whether I should have it in or not, because it's another quite complicated idea, this one due to Giulio Tononi and his colleagues in Wisconsin mainly. And in its full version, the mathematics of IIT get pretty hairy. But it's something I've been interested in working on again for many years, and again have been very lucky to have smarter colleagues with me sort of working on the more technical parts. And actually, this question is very timely. Today, when we were having this conversation, the beginning of June 2022, just had a paper come out this morning in Trends in Cognitive Sciences, led by Pedro Mediano and Fernando Rosas, but with me and Dan Bohr and Adam Barrett, my colleague, is the senior author on it, called The Strength of Weak IIT. And we're exactly trying to lay out very as clearly as we can different approaches to thinking about IIT and what the outlook is for these different approaches. So strong IIT, which is, if you like, the IIT propounded by Tononi and his colleagues, is super interesting. It's a beautiful set of ideas. I find it attractive because it starts with phenomenology. It starts with what conscious experiences are like. It doesn't sort of say, well, this brain region should generate consciousness and let's see if it does or not. It just says, okay, what's the properties of lived experience? And they pick a number of different properties. They call them axioms, but I'll just pick two for the sake of brevity. Every conscious experience we have is integrated. Like there's a single conscious scene at a single time for each of us. But every conscious experience is also highly informative. So every experience we have is unique and it rules out a very large repertoire of alternative possible experiences. These two properties give rise to the name of the theory, integrated information theory. The core idea being that if our conscious experiences have these two properties, well, then the mechanisms that underlie these experiences should also have them. This is an old idea. I first encountered it more than 20 years ago in a paper, 1998 paper from Tononi and Gerald Edelman. And in fact, was so inspired by that's why I actually went to San Diego for my postdoc, because that's where Edelman and Tononi were at the time working. Tononi had left by the time I got there, but I worked with Edelman for a few years. And we, thinking about this idea and related ideas. So IIT takes this idea and it comes up with measures and models of integrated information, and the best known by this quantity phi that represents the amount of irreducible integrated information generated by a system. And it's kind of complicated to measure, but for most systems, you can measure, in principle, there's a level of integrated information you can measure. It'll be often zero. It'll be zero for things that don't interact at all. But for brains, it's not going to be zero. Now, strong IIT is called strong IIT because it proposes an identity between properties of integrated information and consciousness. If I get it right, and forgive me if I don't quite get it right off the top of my head, but proposes that consciousness is identical to maxima of irreducible integrated information. And it's a property of the mechanism of a system, interestingly. It's a property of the cause-effect structure of a system. So not just what the dynamics of a system are, but combination of the dynamics and its underlying structure, which makes some really interesting predictions that, if you keep the dynamics the same, but change the underlying structure, well, then your conscious experience should change, which is a very interesting prediction to make. So it's a beautiful idea and set of ideas, but it has the challenge that in practice, it's very, very hard to measure or to do much with. And this is because of the strength of the claim. It's precisely because strong IIT proposes this identity relation, which is then supposed to solve the so-called hard problem of consciousness, that, this is what consciousness is, in the same way that mean molecular energy or kinetic energy of molecules is heat. There's no, it correlates with heat, it is heat. And so IIT is proposing something similar for consciousness, but because it makes that relationship, there are then some technical reasons why it becomes extraordinarily hard to measure for any real system. And it's also a very strong claim that you might or might not want to sign up to. And our point in this new paper in Trends, and it's a point that we've made and I've made and Adam's made and other work for years, is that there are other ways to think about this. You can keep the core idea of developing measures that try to express core properties of phenomenology, in this case, integration and information, but you can do it in a way that doesn't propose and doesn't rest on there being an identity relation, that one is the same as the other. You can just say, and this is what I call the real problem approach to consciousness, rather than the hard problem. Like, what are the properties of consciousness and what kinds of mechanisms and processes in the brain and body might help explain these properties? And so this is weak IIT, weak integrated information theory, as we talk about in our new paper, is coming up with measures that bear some resemblance to measures of phi and other measures of information dynamics that explain, relate in an explanatorily useful way to properties of consciousness, but which don't make this claim of identity. And again, for some sort of mathematical reasons, these quantities turn out to be, on the whole, easier to measure in real systems. But of course, they make a less strong claim. So what we're really trying to do is say there's a range of options here. You might, and many people do, be attracted by the strong IIT because it promises a lot. It promises to sort of solve the hard problem of consciousness. But you can still do a lot in the space of IIT-like ideas without buying into the whole strong IIT concept. And I think that's useful to point out. For me, it's more attractive. I mean, there's this whole history of thinking of like the strong version of a theory or an idea, and actually the weak version turns out to be the most useful. The title of the paper was inspired by a classic 1973 work in sociology by Mark Granovetter called The Strength of Weak Ties. This is showing that in network theory, you have all these little weak connections between nodes or regions, and those turn out to be super important in understanding the behavior of the network as a whole. And small world networks famously expressed that by Watts and Strogatz. And then you've got the weak AI versus strong AI. Instead of actually trying to instantiate intelligence, we probably make more progress by just implementing some of its properties, and weak and strong artificial life. The same thing argument plays out in many contexts. So it's not weak as in worse. I think it's actually weak as in stronger.
This Bayesian inference framework describes consciousness in terms of computational infrastructure. But to address phenomenology, we need to invoke the notion of controlled hallucination, right?
Yeah. This, so I guess I've just been interested in this predictive processing idea for ages. You can think about predictive processing without dealing with consciousness at all. Many people do. It's just can be thought of as a model of how perceptual systems work that we could test. Are there prediction errors in the brain? Does the brain send top-down predictions? And there's lots of evidence now that something like this is going on. But you can do all this without worrying about consciousness at all. But of course, I'm interested in it because I'm interested in consciousness too. And so then you have to start asking, like, well, okay, how does this speak to the nature of our conscious experience? And the basic idea here, and it's not my idea, is that what we consciously perceive is built from the top-down predictions, not the prediction errors. It's, if you like, the joint contents of the brain's Bayesian best guess of the causes of its sensory signals at any given time. This is where this term controlled hallucination comes in, which, here's a problem with terms like this. If you want to put things in plain language, there's never an ideal set of terms to use. There's never the ideal words. They can all be construed in different ways, but you've got to use some word. You can't just leave everything as equations and boxes and arrows and whatever. So controlled hallucination is the term I use. I heard about it from Chris Frith, who you've spoken to, I think, already, who heard about it from someone else. And Actually, I've been trying to trace it back. Where did it originate? And it seems to go back at least to the 1940s. The reason I use it is because it underlines that normal perception really does come from within in this view. It's an internal construction, a best guess about what's out there. And so there's a continuity with what we would typically call hallucination. What we typically call hallucination is when people experience things that are not there or that other people don't. And it's tempting to think that's a totally different process from normal perception. But we know of gray areas. Like you look at a cloudy, this sort of day when there's little fluffy clouds, and you might see faces in these clouds, or in a piece of toast. Our brains project patterns into things. We might hear a voice when there was nobody there. It's quite common. So the idea is there's in fact a continuity between hallucination and normal perception. The key difference is in the control, hence controlled hallucination. Our normal perceptions are tightly related to what's out there in the world. They're controlled by the sensory signals. So you can then think of hallucination as a kind of uncontrolled perception. So they're two sides of the same coin here.
One additional question you have not explicitly written about in the book, but I would like to know your stance about is what is ontological status of information? Some philosophers like Dan Dennett claims that information is a whole different category, like we have matter, energy, and information. Do you agree with that, or do you have a different approach?
Well, this gets us a little bit back to the integrated information theory. So information is a very interesting and tricky concept. I mean, we colloquially use it all the time. You read a newspaper, you get information. We use it quite loosely when we talk about the brain, and especially when we're making analogies between the brain and the computer. A lot of people in cognitive science would just say, obviously, the brain does information processing. That's what brains do. There's nothing obvious to me about that at all. It depends on what you mean by the terms. And the brain, you can make an analogy between a brain and a computer, but it doesn't mean the brain is a computer. And in fact, I think most neuroscientists would demur about that and say, no, the brain isn't a computer, but yes, it does information processing of some sort. Why is it a problem to use it loosely? Well, there are at least two senses of the word information here. There's the use that's most standard in information theory due to Claude Shannon, which is, you would say, it's kind of observer-dependent information. Like it's all syntax and no semantics. Right. And the origin of information theory was how to send messages more reliably in an error-free way. But you need an encoder and a decoder on each end to make sense of these messages. So yeah, when the neurons fire spikes, you can describe these in terms of information theory, but do they really mean anything to the system itself, or is that just a way of doing statistics? Yeah. That's a typical way. We think we use information in most applications, and so you need an observer, you need some interpreter. But there's another sort of perspective on information, which indeed, as you mentioned, gives it a status that's much more fundamental to our picture of the universe. And here we get into sort of deep issues of the foundations of physics, not just cognitive science and neuroscience now. Does information exist in the same way that sort of mass, energy, charge exists? John Wheeler famously expressed this idea in what he called the it from bit hypothesis, that in fact information is more fundamental and everything else comes from information. Do I agree with this? I am agnostic about it. I think it's a distinction that's very important to make and to recognize. So the reason this relates to the IIT discussion is that IIT in some sense relies on this strong ontological interpretation of information. It's sort of because it's making this identity between a property of information that's not observer dependent. It's intrinsic to the system. And Tononi and others will rightly make the point that being conscious doesn't depend on whether somebody else is looking at my brain or not. It's just it's a thing. Brains are conscious or not, and so to make this identity relationship between integrated information and consciousness, you kind of have to assume that information, at least in its integrated form, exists and is not just something that observers describe. This is actually why it's really very, very hard to measure. Weak IIT does not make that assumption and relies on a more standard Shannon version of information and information dynamics, which just allows us to describe things like integration and information in a way that is still explanatorily useful, but doesn't make this claim of identity. But anyway, just to head on answer your question, I find it fascinating, but I'm agnostic, and it's a little bit, I don't feel remotely qualified to pronounce on that, because that really is a question about sort of fundamental physics. What's really out there? What's the nature of the universe? And of course, that's still basically unknown. What is it? Superstrings? Who the hell knows?
Yeah. Or I'm more sympathetic to quantum loop gravity than superstring. It is more in principle, seems more in principle verifiable than superstrings. One thing that follows from this, if we consider that information processing is not just a convenient metaphor or a model of speaking about consciousness, it logically follows that it could be realizable in artificial system. But you claim that we don't have knockdown argument for that artificial consciousness.
Yeah, again, I'm disappointingly agnostic about this, and I'm very suspicious of people who make strong claims one way or the other. I mean, there's this idea, at least implicitly out there in a lot of writing and thinking, that artificial intelligence is on an inevitable trajectory towards artificial consciousness, that there'll come some moment where AI systems reach a threshold of intelligence. And this is often equated with what's called general AI, so the general capabilities of a human being. And at this point, or maybe some other point, the inner lights come on and this system is conscious. There becomes something it is like to be that system. There's two things that I worry about with this line of thinking. The first is the idea that consciousness is a function of intelligence. I just don't think this is true. I think intelligence gives us different ways of being conscious, but I don't think consciousness just comes along for the ride as levels of intelligence get higher. I think the origin of this idea is rooted in human exceptionalism. This idea that we humans are smart and we're conscious and we want to be special, and so consciousness and intelligence go together. But of course, many other creatures, they're smart in their own ways too. It's also very questionable whether we are the smartest creature around. In some ways, yes, other ways, definitely not. And the most fundamental kinds of experience that we might have are very closely geared to basic survival needs, things like disgust, fear, hunger, thirst. You don't have to be that smart to suffer. You just have to have a body. And so this is the other thing that causes me to suspect this line of thinking is, why should consciousness be assumed to be substrate independent? So by substrate independent, it means that a computer programmed the right way could be conscious. But if it was substrate dependent, maybe it can't be. It really depends on what the thing is made out of. So if you assume that consciousness is a form of information processing, as is often done, well, that smuggles in this assumption of substrate independence. Like, information processing can be done on all sorts of systems. But again, as we've said, I just don't think that's a
have to assume functionalism first to draw a conclusion of substrate independence.
Say again?
We have to assume that functionalism is absolutely true, hard version of it, that it does not matter which substrate information processing happens inside.
Right. So there's actually two parts to, as I understand it, there's two parts to functionalism. One as a theory, or a philosophical perspective on consciousness. One part is that the substrate doesn't matter, substrate independence. And the other part is that all that matters are the input-output relationships, like the function performed by a system, not necessarily how it's doing it. The two things are actually slightly different. And one context in which you can see they're different is again, integrated information theory. Integrated information theory is substrate independent, but it doesn't fit with a second assumption. For integrated information theory, the underlying mechanism has to be a particular way, even though it can be made out of tin cans as much as it can be made out of neurons. So there's a nice paper in 2015 by Giulio Tononi and Christoph Koch, showing that you could have a big feed-forward neural network, would not be conscious. There's no integrated information, but a recurrent network that has the same input-output mapping would have some integrated information. Anyway, there are distinctions, but fundamentally, for me, I just think it's a little bit ungrounded, unsupported to simply assume that consciousness is substrate independent and that it's something that can be, for which simulation is the same as instantiation. And there are some things that if you simulate them, it's equivalent to the thing. A computer that plays chess actually plays chess. But there are other things where that's not the case. A computer that's simulating a weather system, it doesn't get wet. Rain is not substrate independent. It requires H2O. And so those are negative reasons. On the other side, the whole line of thinking connecting us back to the free energy principle really puts life at the heart of consciousness. And the whole reason we have this conscious experiences of self and of the world in this view are because we are living creatures. And there's no clean separation in a living creature between the hardware and the software. Where do you draw the line in a living system at which you've got like the substrate and stuff on top of the substrate? It's really not clear. So I'm agnostic, but my suspicion is, for these reasons, that the substrate does matter and that consciousness may turn out to be a property of living systems. And that's, in philosophy, that's a perspective of biological naturalism.
Thank you very much, Anil. It was very interesting.
Oh, thank you. I mean, thanks for those really good to dive into the detail on those questions. So it's a real pleasure, and thanks for inviting me.
Thank you. Bye.
Okay, great. You made it. So yeah, just send me a link when it's out.
I'll send the link, and afterwards I will make Georgian transcript, which will be published in local magazine, and I will send it later too.
Okay, perfect. Thanks so much. It's really good to speak to you. Have a good day.
Bye.
Bye-bye.